Welcome. In this session, we'll continue with the discussion on solution of differential equations. Let's start. Now, let's solve one practical physical problem. That's the harmonic oscillator. Now, how do you obtain a harmonic oscillator in physics? The physical model, if you have a spring that has a spring constant K and mass M, you can attach the mass to this spring and connect the whole system to a wall that is shown here. And if you displace this mass by some amount, you know the behavior of this mass will be governed by the differential equation like this. It will be x d2x of d square kx will be equal to 0. If we assume the friction here is 0, so the friction here is 0, this is the differential equation. So this is the differential equation that governs the behavior of this mass that you have displaced by some amount d. All right, we know from differential equation cos the solution of this differential equation will be simply x of t is the second order differential equation cos omega naught t plus b sine omega naught t. So this is the differential equation this is the solution of this differential equation. All right. So because this is a second order differential equation, so this will have two constants, a and b here. Now, if you solve this for a particular case, means if the initial condition, suppose initial value means the initial position of this mass is at 1, and you can say the initial velocity x dash is equal, this is the derivative of x at t equal to 0 is 0, means the initial velocity and the initial speed is 0. Then the solution of this differential equation is this. So the solution a becomes equal to simply 1, b becomes equal to y. Remember, omega naught here is right. So this omega naught is this damping, this natural frequency is equal to under root of k by m. So this is the solution of the second order differential equation that governs this system. See, this is the analytical solution. You can obtain it in mathematics. This is not the goal of us to solve the solution. So to solve these differential equations analytically, our goal here is to solve these differential equations in Simulink. Now let's see how do we solve this differential equation in Simulink. Let me rewrite this differential equation in this notation. So x double dash, and then kx will be equal to 0. Now we can rearrange the terms. We can write the highest derivative on one side, kx divided by m. And let's take, for simplicity, let's take k equal to 5 and m equal to 2. For simplicity, let's take it equal to this. So k is 5, m is 2. Let's solve this differential equation. Now you can see how many, the highest derivative here is 2. So there will be 2 integrator blocks will be used in Simulink model. So we require 2 integrator solve this differential equation. And let's take the initial condition same, x of 0 is 1, x dash 0 is 0. All right, let me switch back to MATLAB to show you the solution. So you can see the solution looks sinusoidal or cos. So the solution is cosinusoidal here. Let me switch back to MATLAB to show you how to solve this. So let me open Simulink. If I click on the Simulink tab, a window pops up. You know, the window will pop up that looks like this. So this is the window that appears there, and I hope this is visible. I have to switch to this screen again and again. Please bear with me. Then click on the Simulink library. After you click on the Simulink library, this window pops up there, and what I require is the gain block. So this is the gain block. Then I want to see the result also, plot the result, and I need 2 integrator blocks. Add. Now let me show you the blocks that I have added to this model. So this is integrator, this is integrator, then I have scope, and I have a gain block. How I am changing the direction of this gain block, just click on this block, then click on Control R simultaneously. So if I say input is X double dash, then the output of this block is simply output is X dash, and then you can click on this, and then connect to this, and this is our X. So this is our X, and the initial conditions are X of 0 is 0, X dash of 0 is 0, and X of 0 is 1, and this is minus K by M. Gain is minus K by M. Minus K is minus 5 by 2, and this is the response. So this is our X dash, and this is connected to this. All right, so let me click on this configuration block to change the step size, to show you how to change the step size. So I'll use the step size is 0.01 this time. Click on apply, then go back to the model, and this is the model. Let me run this model. Let me show you the result, and you can check indeed this has a sinusoidal response, this differential equation. Now, why it's called a harmonic oscillator? Why the name harmonic oscillator? You can say this has the harmonic and output is the harmonic response. And the response, if you change the position of this mass, it will oscillate, and the oscillations looks like sinusoidal. That's why it's referred as harmonic oscillator in physics. That's why it's referred as harmonic oscillator physics. You can say it does this. The periodic motion means the motion is periodic, and we're assuming that the frictional part of this is 0. We are not taking friction into account. So when we do not take the friction into account, this will always oscillate. Means there will be no damping of this. That we will do in the next session. I hope you understood the concept. This is the response of a harmonic oscillator. All right, let me end it here. In the next session, we'll learn the response of solve the differential equation if we add one more term to it, to the harmonic oscillator.